The next unit we're going to do is energy and momentum, so we're going to start here with a discussion about energy. So what exactly is energy? I think everyone has somewhat of an idea of what it is, but to actually go ahead and define it can be a little bit tricky. So if you go and look in a textbook, you're going to find a definition for energy that's probably something along the lines of this. Energy is the ability of an object to do work. And then you might think, well, okay, let me figure out what work is. If you go and you look up work, you'll find that work is the change in energy. This doesn't really help. This kind of sends us in circles. It doesn't really help us understand the meaning of either energy or work, and I don't particularly like either one of these definitions. The definition that I like is that energy is the ability of an object to change itself or to change the world around it. And if we think about energy and think about some of our examples, all right, I think all of these fit into this definition. Right? We might say that an object that's moving has energy. Well, that moving object, all right, can crash into something else, can collide with something else, and thereby changing the world around it. All right, another example of energy is a lot of people talk about potential energy, right? We have some object up at a height, okay? That object up at a height can fall down, all right, and start moving faster, all right? That would be an example of its energy changing something about the object itself. Okay, so all of these things fall into this definition. The energy is the ability of an object to change itself or the world around it. There's a lot of different kinds of energy. We could spend the entire year talking about energy. We're actually going to focus on one specific type for now, or one specific category, and that is mechanical energy. All right, and that's going to be the energy of motion, the energy that you're probably most familiar with, kinetic potential, and we'll talk about all of that in a second. The standard unit for energy is the joule, okay? That's what we're going to use, just abbreviated with a capital J. Calories are also a unit of energy, which you see on food nutrition labels. That also is quantifying the energy that you get from eating that food. But our standard unit here is going to be joules. So this list here is very, very far from a complete list of all the different types of energy that we have, but this is going to be what we're going to focus on for now. So we're going to talk about kinetic energy, which is abbreviated with just a capital K, two different kinds of potential energy, gravitational potential energy, UG, and spring or elastic potential energy, US. Potential energy in general is abbreviated with a U, so that subscript is just going to distinguish between the different types of potential energy that we have. We're going to talk briefly about heat, and we're going to talk about work as well, which are kind of like types of energy, as you'll see in a second. First type of energy we're going to talk about is kinetic energy, and kinetic energy is simply the energy of movement. So anytime something is moving, spinning, oscillating, whatever, it's going to have kinetic energy. And you're going to see that as we go through this unit, we're going to have to kind of change how we think about the world a little bit. We're going to have to think in terms of the world of energy. And from now on, whenever you see moving, you instantly want to be thinking that that moving object has kinetic energy. Okay, that needs to be something that becomes automatic here. Sometimes you hear kinetic energy referred to as the energy that you can see, because it's very obvious, very apparent if an object has kinetic energy, because we just need to look and see whether or not it's moving. Right? The way we calculate the amount of kinetic energy is given by this formula here. K is equal to 1/2 mv squared. So K is our kinetic energy measured in joules, of course. M is our mass, and V is our velocity squared. Okay, so you can see for an object to have kinetic energy, all we need is a velocity. The next type of energy that we're going to talk about is gravitational potential energy. Let's for a second, though, talk about what potential energy is in general. So potential energy is stored energy, energy that can be used later. And this would be an energy that we can't see. Okay, the way I always think about this is if you have a ball sitting on the ground versus a ball sitting on the hill, those two balls look the same. But there is a key difference, and the key difference is that the one up on top of the hill has some potential energy, has some energy that is stored that can later be released, all right, as the ball rolls down the hill and turned into a different kind of energy. So that's what potential energy is in general. Gravitational potential energy specifically is the energy that results from an object being some height above the ground. And that's going to be the key for gravitational potential energy, is that we have a height. All right, so from now on, when we're in energy world, anytime you see something having a height, that's immediately going to indicate to you that it has gravitational potential energy. The way we're going to calculate our gravitational potential energy is with this equation here, UG equals mgh. So U sub g is our gravitational potential energy. M is the mass, g is that acceleration due to gravity, which is 9.8 near the surface of Earth, and h is the height above the surface. Okay, so that's going to be how we calculate our gravitational potential energy. One quick note here that seems like a little bit of a subnote, but it is something that the AP exam actually emphasizes a lot for whatever reason, and that is that gravitational potential energy is an energy that exists between an object and the Earth. Okay, technically an object by itself cannot have gravitational potential energy because that energy wouldn't exist without the Earth. All right, kinetic energy an object can have by itself. If it's moving, that object by itself has kinetic energy. But gravitational potential energy is an energy that exists between the Earth and the object together. Okay, the Earth-object system. So you will see that pop up from time to time. Whenever they're talking about gravitational potential energy, it will always be the energy of the Earth-object system. Okay, small little technicality, but like I said, it is something that for whatever reason is emphasized by the AP. Next we have elastic potential energy or spring potential energy, which is the energy associated with a stretched or compressed spring or elastic band. Okay, and so the key thing here is from now on, whenever you see something about a spring, that's going to immediately indicate to you that you have spring potential energy. The way we calculate it is US equals 1/2 kx squared. So U sub S is our spring potential energy. K is our spring constant, so that's going back to the forces unit. K tells us how strong the spring is, all right? The higher the spring constant, the stronger the spring is. And X is the amount the spring is stretched or compressed, all right? One side note with this one as well, much like with gravitational potential energy, objects by themselves cannot have spring potential energy. It's an energy that exists between the object and the spring together. Okay, just like with gravitational potential energy, it was between the object and the Earth. So whenever we talk about it, we're going to talk about the energy of the spring object system. Same basic idea, technicality, but it's something that the AP emphasizes. Let's do a few quick practice problems with those three types of energy. So we'll start with this. We have a 0.003 kilogram penny sitting on top of a 1,400 meter tall building. We want to find the energy of the penny Earth system. Well, that's going to be a gravitational potential energy, right? The penny's not moving. There's no spring. The only type of energy it has is gravitational potential energy due to its height. And so we're going to go ahead and plug in the mass of the penny, G, which is 9.8, and the height of the building, and we find that the gravitational potential energy of the penny Earth system, because remember it's between those two, is going to be 41.2 joules. For B, a box is compressed against a spring. The spring system stores 4 joules of potential energy. If the spring had a spring constant that was twice as big, but it was only compressed 3/4 as much, how much energy would be stored by the box spring system? So we're clearly thinking about spring potential energy here. And this is going to be one where we're going to go ahead and set up our new and our original. So our original, we know we store 4 joules of energy with it, and that's going to be equal to 1/2 kx squared. For our new one, we don't know the energy we store. That's what we're looking for. We do know, though, that our spring constant is now twice as much, so it's going to be 2k. And we compress it 3/4 as much, so times 3/4 x, that entire quantity squared. So when I go ahead and do a little simplifying, I get that this is 1/2 times 2k times 9/16 x squared. There are a few ways of doing this, a few ways of combining this. What I'm going to do is I'm going to pull those two constants out in front. Okay, so I'm going to say US is equal to 2 times 9/16, and then what's left is 1/2 kx squared. And the reason I did that was this here was simply equal to that original piece. So what I end up getting is that my spring potential energy now is going to be 2 times 9/16 times 4, which leaves me with a spring potential energy here of 4.5 joules. Alright, moving on to our last one, we have one with kinetic energy here, and once again this is one where we're going to start with our kinetic energy equation and set up a new and an original. So our original is just going to be that K equals 1/2 mv squared. Our new situation, we're now going to triple our velocity. Okay, so I'm going to say K prime equals 1/2 m times 3v, that entire quantity squared. Go ahead and square that 3, so K is 1/2 times m times 9v squared. And once again, I'm going to pull out that 9 out in front here. Say K is 9 times 1/2 mv squared, which I know is equal just to my original K. So I can say K prime, that new kinetic energy, is 9 times my original.